Good day, everyone. Today we're going to be treating physics, and we have a question here. The question says that montrez que le mouvement décrit par les équations paramétriques x de t égale à cosinus t au carré in meters and yt égale à sinus t au carré also in meters. Equation parametric in English means parametric equations, the parametric equations that we are already used to. So here they are saying that we should prove that the movement described by this parametric equation in the system of coordinate Cartesian, that's the Cartesian coordinate, OX, Y, est circulaire uniformément accéléré. So this is what we are looking for, okay? And just right here we're having a rappel where it states that when parametric equations contains trig functions of a time variable, a variable t, we can have, for example, x of t equal to cosinus x of t is equal to cosinus t square, and y of t is equal to sinus t square, so that we can have x square plus y square equal to cosinus t square square, because we know this relation in a trig function will give us 1. So what I'm trying to say, why I introduced this particular case for trig functions is because of what we are having in our question. We should prove using the parametric equation. So here we are in cinématique de points. Now we can also try to go back to our rappel of coordinate Cartesian. Don't get confused, it means the Cartesian coordinate. For example, if I have coordinates xy, I just do a little space here. I have a coordinate xy. I'm not doing it to scale, it's just good. Yeah, we have y here, we have x, we have a negative x, or maybe sometimes you see this x prime, and we have y, negative y, or sometimes you see this y prime. That shows this side you're having the positive for x and y, positive y, negative x, negative x, negative y, positive x. Now this is how we describe Cartesian coordinates. Like, if it's just like you'll be given a particular point here, and then you trace from your y-axis, your x-axis, whatever you have here and whatever you have here, you put it in brackets x comma y. Order is important. You can't have it as y. If it's in this case, you can't have, if let me say this is a 2 and this is a 3, I can't say this is equivalent to 3 comma 2. It's wrong. It has to be 2 comma 3. So this is just how coordinate Cartesian is all about, like just something like this, just to give you a little bit of rappel. So now we can come back and answer our question. So our question, we are asked to prove that the movement described décrit par les équations paramètres x de t, which we have this relation here, and then in the system of coordinate. So what we can start with, we are actually remember. Okay, remember, like from the rappel I said, remember that we have x square. I should highlight this. Okay, x square plus y square is equal to cosinus t au carré plus sinus t au carré equal to 1. Remember this, yes? And since we are going through the coordinate Cartesian, we're starting from x and y. The next thing we're supposed to do here is we're going to derive x and y to get our vector vitesse using for Cartesian composite Cartesian. Sorry. So we're going to have to derive our x of t and our y of t to get our vector vitesse. After that, we are going to find the module of our vector vitesse. So let's start with deriving x of t and y of t to get our vector vitesse v. So our vector vitesse, it's vector vitesse. So we are going to have the v-test sign just above it, and then our x of t is cosinus t whole carré, and then so deriving v of x, it's going to be d of x over dt. Okay, and deriving this, what are we going to get? We know that the derivative of cosinus is negative sinus, is negative sinus, and then we have t whole carré, so we'll bring our 2 here, but because it's going to change to sinus, that's negative sinus, we're going to have a negative. Then we bring our 2 here, we're deriving, remember that we bring our 2, our t, and then our sinus t whole carré. And in this case, since we are now deriving vector velocity, it's going to be meter per second. We apply the same thing for vy. We have dy over dt. We derive the same thing. We have our 2t, and the derivative of sinus is cosinus, so we are going to have cosinus t squared meter per second. Yes. And the next thing that you're supposed to do is to find the module of a vector v-test, that's v. So finding the module of the vector v-test, it's v. I'm having a little problem with my black pen. Okay, so we have finding the module is just like finding like the Pythagoras, where you get the two parts and then you have c, then you find a squared plus b squared, almost alike, just that this is vector v-test, but the same manner of solving. Okay, so we have v, vector v-test, the module, so I did this, the module, okay, of vx squared plus vy squared. So if I do the vector of vx squared, the module of vx squared plus, like I calculate vx squared plus vy squared, what am I going to have? So at this point, we are going to replace our vx and raise it to the power of 2, and then our vy and also raise it to the power of 2. So we are going to have alright, so we'll have negative 2t sinus t squared, everything raised to the power of 2. Then our vy, we have 2t cosinus t squared, everything raised to the power of 2. Then finally, we still with our square roots. And then we have this, I can break it down to minus 2t squared sinus t square plus 2t square cosinus t square. And then what would this give us again? We're going to have this is minus 2 square, that's 4t square, that's 4t square, and then sinus t square plus same thing here, 2 square, that's 4t square. Alright, okay, that's fine. And then cosinus t square. Note that I always try to put this so that you will know that we are still in the squares, because if this should leave the square, that means you're working with the other part, but then the one that is not in the square root is not part of the square root. Okay, so okay, this, I just put this a bit here. Cool. All right, so I can factor out 40 squared because I have them together. So what are we going to have at the end? We're going to have 40 squared, right? And then sinus t square plus cosinus t square sinus t square plus cosinus t square from our trig functions. We have here cosinus, we mark that x square plus y square, cosinus t square plus sinus t square is equal to 1. So this entire thing we have here is equal to 1. Okay, So what are we left with? I just do it right here. So we are left with 4t square, and the square root of 4t square is 2t. So finally, the module of our vector v test is equal to 2t. I think I'm having a problem with my pen. Okay. All right. Well, that's okay. Then that's for the first part. Then the next thing that we're going to have to find is the composant de l'accélération. The composant of the acceleration. That means we're looking for the x and the y. That's the ax and the ay for acceleration. It's still going to be in vector. And then we can guess, like, let's just give a little rappel. I just do that quickly. Here we have, like, we are going from the position, we are going to v test, then to acceleration. So what do? We are deriving. We derived v, we derived x, we got to v. Same thing, we are going to do that acceleration. So we're going to find for the two components ax, ay, that's ax and ay, we're going to derive this two components to get our acceleration for ax and for ay. So just like we did, we are going to write our acceleration in a vector form, and then we have this, and then we have ax, we have ay. So we are deriving dvx over dt and dvy over dt, right? So for the first one, we had vx was minus 2t sinus t square. So we are going to have to derive minus 2t sinus t square prime. And then for vy, we had 2t cosinus t square. So we are going to have to derive these two. So deriving this, we are going to use, so if you can remember, when deriving product, I have uv, for example, we're asked to derive product. So it's u prime v plus v prime u. That's, you derive u, leave v, plus derive v and then leave u. So in this case, I'm going to call my u negative ut, and then my v sinus t square. Same thing here, my u and then my v. So we apply the same rule, okay? So what are we going to have? We're having this, so our ax, let's just do it here so it will be clear for us to see. So our ax would be deriving the first one, that is deriving u, derivative of my negative 2t is going to be negative 2, and then we leave our v, that's sinus t square, then plus derive our v, derivative of sinus is cosinus, right? So we're going to have cosinus, okay? Then our t square, we bring it back like how we've been doing t square, and then this is t square. Then we leave our u is negative 2t. So finally we have negative 2 sinus t square, negative 2t times 2t, that's negative 4t square. So that's negative 4t square, and then cosinus t square. This is for ax. Then for ay, we have the same thing. We apply the same logic here because it's uv prime. So we derive u, derivative of u, we're going to get 2. Then we leave our v, which is cosinus t square. Then plus, we derive the v, the derivative of cosinus is negative sinus, so we know here we're having a negative sinus. Then t square, which will bring and have 2t, and then t square, and then we leave what our 2t was initially, which was a 2t, right? A 2t. So finally, what do we have? We're having 2 cosinus t square minus 2t times this, that's negative 4t square sinus t square. So we have negative 4t square sinus t square. So this is what we have for our